welcome to another day of CS 219. Today we're going to be talking about chapters 9 and 10 that involves the operating system, and chapter 10 is basically a quick overview of what you should have learned in CPE 100, which is binary and hex. So we'll kind of go over that very briefly since we should all know that at this point. So, but before that, let's talk about operating systems. So we are going to go a little bit quickly through this chapter because, as you can guess, if you have looked at a course list of as a CS major what you're going to take, you will notice that there is a class that is CS 370, which is actually called operating systems. So really, what you're going to get today is more of a taste of what that class will be like, and I'll try to make some points about that as I go over to kind of, tell you what will be covered and other things like that. So, don't feel disappointed if we're kind of rushing through this, because again, pretty much everything that I will talk about today will be covered in extreme detail in that class, to the point that it's an entire course. So like, imagine one chapter of the book basically being an entire course, and that's kind of what you get when you get 370, which is kind of like the follow-up to this course in a way. So what is an operating system? Let's start with that basic thing. And so an operating system is a program that controls the execution of application programs and acts as an interface between applications and computer hardware. So in layman's terms, so far, when we were doing like the IS computer and things like that, we had a bunch of instructions that we were directly sending to the CPU, right? But those instructions, that architecture is basically, like multiply and add and things like that. But if we had something like an IO operation, we say something like operation IO, some specific opcode, and then things happen, right? But essentially, there needs to be, as you can see, when we have multiple programs and multiple processes and multiple hardware, we need to have a special program that basically connects or interfaces between an application and the computer hardware. So if you are trying to print to the screen as a programmer, you don't need to actually write code to generate the image in the screen, like from the terminal, right? Imagine if you had to do every single piece when you were writing a program. So instead of saying in C++ something like cout, hello world, or doing the equivalent sort of print command in assembly, imagine if you actually had to code a interface that could actually generate an image into a screen, and in that image you could generate the right organization of pixels to generate the text that you're trying to do. That would be extreme amounts of work for something so simple. So as a programmer, you want to kind of, make usage of all the hardware available to you without having to code every single functionality of it. Imagine if in your programs, when you were just trying to do a simple calculator, along with the calculator code, you had to write code for how the cache was working, how the main memory is working, communicating with the hard drives, basically how to read input from a keyboard, like actually be able to transmit and to transfer the signals coming in from the wire into actual valid keyboard presses and things like that. That would just be way, way too much work when you're just trying to write a single program, like a CS135 program, like a calculator. And so we want to have convenience, and that's going to be the big thing about operating systems, is you want to have a convenience to make a computer easier to use, and you want to make it efficient, because if you're writing all this code by hand, while yes, you could make it amazing, it's going to take you forever to write a simple hello world program. And furthermore, when you're writing programs, you want to be able to write them quickly, but at the same time, you want it to be good, and you let somebody who knows their IO devices properly to write that code, and who knows how to connect or do the caching system to write that code, and you not have to worry about that. And so the OS, operating system, is just going to be another program that basically handles this, or a collection of programs that is essentially sort of providing services in different areas. So what are the kind of areas or features that an operating system should ideally have? And those are going to be the following. And there's a list in the book right in the beginning, so we'll just kind of list them and talk about each of them. And so we have program creation. In fact, let me go ahead and write them first, and then I'll talk about them. And in the meantime, I want to say that one of the big things about operating systems is going to be not just that they can do all these things, but that they mask them even from you. So like, you don't even have to worry about it. You know, all the details of the hardware, you know, those things are masked from the programmer, and it provides the programmer with a convenient interface for using the system. So it's sort of a black box that you just tell it to do things, and it does things, and you don't have to worry about how it does it. You know, it's a little bit like when you were talking in CS202 with object-oriented programming, and you know, like the idea of data abstraction and things like that, where you know, you have a black box that does things. You know, you have a function that says something like you know, print this, or just a function called print that's part of a class, and you don't have to worry about how that gets done, but you just know that it will print things out, you know. So and then, you know, we got like polymorphism and all these great things. So kind of think of in those terms when we're thinking about the idea of masking. You know, I don't need to know about all the cache implementations in my computer. I mean, as you guys can kind of guess, you didn't have to think about caching in CS135 when you were writing some basic programs, or in 202, right? You don't have to think any of that. The most sort of low-level thing you had to think about was like when you were doing assembly stuff, and you actually had to move things around in registers. But even in that case, you still did not deal with anything related to cache, right? Or how things were being read from memory. That was all done behind the scenes. So even at the assembly level, you know, there's a lot that you're not seeing there happening. And, you know, you might think of, wait, you know, registers are the most basic level. That's even lower than cache. Yeah, sure, but you got to realize something that we're going to talk about in a minute here. There's more than one program running at a time in your computer. And, you know, if one program took over the processor entirely, then you would not see anything happen in terms of like your computer would basically freeze. You would not have an image that refreshes your screen, or basically you know, keep something as basic as keeping your fan spinning. Sorry, I heard a noise. I was just quiet to listen. What was that? I think that was my dog. But yeah, so all right, I want to finish this. So let's talk about each of these. So these are all going to be the services that you kind of want a operating system to provide in one way or another. So the first one is going to be program creation. And so what you want is the operating system to provide a variety of facilities and services, such as an editor or a debugger, an IDE, and whatnot, to assist you in actually writing code, you know, visual code and those kind of things. And these services are in form of utilities as well that may not be part of the OS, but are accessible through the OS. So you have programs that you can access through the OS. Or more internally, you know, you're thinking like Valgrind and things like that. You know, you want the OS to facilitate you with writing more code by having these programs available. They don't have to be part necessarily of like the built-in OS, but it's nice to have them there. The bigger one, the more important thing that an OS needs to have is program execution, which is there's a series of steps that need to be run in order to actually go from, you know, you typing in ./a.out and actually your program actually running. So basically, you know, you have to load the data and the instructions to main memory. There's I/O stuff that has to be initialized and transferred, and things have to be prepared. And the OS is handling all this behind the scenes so that actually when the program starts running, everything is ready to go. And also supports the program when it's running, because if the program needs to access an I/O device, the OS can hook you up. You know, the OS is like that guy that hooks you up with everybody that you need. So like, you know, you need a printer, the OS is like, don't worry, I'll hook you up. That way, you don't even necessarily have to access the printer directly. The OS is like, no, you tell me what you want me to do, and I'll go tell the printer guy to do it, you know. He's the facilitator per se. So that's kind of the third one as well in there. And so the OS is going to take care of all these details so that you just tell the, like, what you want you tell the OS what you want the I/O device to do, and he'll take care of dealing with the OS and the I/O and handling everything it needs to do with that. Another big feature or necessity of a OS is the ability to have control to accessing of files. So, essentially, you want to. There's two things. You want to provide security to files, so by having some sort of protection mechanism to control who can access files or not. And I'm not just talking about putting a password to a file or encrypting it, but more of like so that a program doesn't accidentally delete something that it shouldn't, right? So if a program is trying to, if you have like we will talk about virtual addressing all in a second, but like suppose, from what you know with addresses that you create a pointer and you set some address that is really bad, like address 5, directly, and you compile with F permissive, so it lets you compile. And then you actually go in address 5 and change something. And address 5 was something related to a completely different program. Now you broke the program, right? So that we don't really want people to do that. We don't want programs to break other programs. So we want to limit what they can access when they're running or not. Further on from there's certain files that are only useful for the operating system and no individual program should have access to. Protected files, like think of Windows and all the Windows files that actually make Windows work, or Macintosh or Linux. And so we want to control basically access to that. In addition to that, ability to access external devices, which kind of goes into the I/O nature. So like disk drives or magnetic tapes, if you have those, controlling access into those drives, you want to do that as well through the OS. You don't want to directly access the drives in the program. Yet again, like the I/O, the OS is going to be that middleman where you don't, instead of talking to the hard drive directly, you talk to the OS and you're like, hey OS, I need this piece of information that's in this drive. Can you please get it? And the OS is like, don't worry about it. I'll take care of it. I'll be back. And then it goes, the OS talks to the drive. He's like, I need this. The drive gives it to the, per se to the OS. And then the OS comes back and gives you access to that. And so there is that control of files accessing for both security and ease of programming as well. Next, we have what's known as system access. That is going to be kind of like you're logging information to a computer. And so, a computer may have different services and resources available to it, and you may not want to give those resources to anybody. You want to control who can use a computer to avoid unauthorized access to information or the computer itself. And so, the system access is basically the OS is putting a wall with like a security checkpoint, in like an airport or something, and it's gonna check you and passport or whatever and make sure that you're actually there because you're gonna fly in a plane, or in this case because you're actually gonna, if you're trying to access the computer, do you have permission to use the computer? And further on from that, and a little bit more specific to an OS, when we're talking about multi-programming, is the idea of resource contention. So you may be running multiple programs that are all trying to use a specific resource, such as an I/O device, like a printer. You might have like Microsoft Word open, Firefox, and PowerPoint all open, and all three of these are trying to actually print something out to a printer. Like for example, while the printer might have its own sort of embedded system that can handle all those requests, it's nice to have the OS to sort of be that middleman as well, because it can prioritize as well, because it might be more important to print out the Word document, or because that one was the first one that actually was requested and it wants to keep some sort of queue. So system access is also related to accessing resources when there's resource contentions, or when multiple things or multiple programs or multiple parts of a computer are trying to access the same resource. And finally, error handling, essentially. Error handling is going to be both error detection. So when we're talking about like Hammond code or parity bits and things like that, the OS is the one that's going to be basically figuring out if something went wrong in communication. And also when there's a violation of things above it, like to system access or things that shouldn't happen, the OS is going to basically detect that and handle it, so that the computer doesn't just like hard freeze and completely shut down, or just get locked up and then you gotta like unplug it basically. Other kinds of error detection is, again, if you're trying to access forbidden memory locations, like things that don't belong to you, or also could detect basic things like arithmetic errors, like division by zero, or arithmetic overflow, device failure. So like, if one of your drives just dies and it stops losing communication, you want that to be alerted to the user. So the OS is the one that's monitoring the health of the devices, and of course, if it stops receiving sort of a signal from the I/O device, we talked about yesterday about the I/O devices having status signals like ready, busy, and so on. If there's no signal, if it just goes offline, then the OS is like, oh, okay, are you okay? Do you hear me? And then the guy doesn't respond, the hard drive, and it's like, well, rip, and then it tells the user like, hey, this guy stopped responding. I don't know if he's okay. You should go check if your computer's on fire or not. So so all that error detection and response also. Response being important because some errors you can recover from, like a program crashes, and it's going to terminate that program because it's frozen or something, and it closes it, right? So by doing that, you recover usage of your computer. Otherwise, you basically froze your computer and you have to reboot it, right? So there has to be some sort of response that the OS can do. And I guess that one extra thing at the bottom here is accounting. So basically, the OS wants to collect statistics and usage in general for various resources and monitors performance and parameters, which can be useful to anticipate the need for future enhancements and for tuning and performance and whatnot. The book does make a weird thing about you could also use it to bill people for resource usage. So that could be Amazon cloud services, how much power you're using. It depends on how much they charge you, how much computing power you're using or storage space. So there's a legitimate requirement for an OS to be able to keep track of that as well. So that, when you open Control Task Manager in Windows and you're looking at the different processes that are running, because your computer is running slow, you can see hey, Chrome is taking a lot of memory, so what's up with that? So all that monitoring is also useful for an OS to have, because it helps you figure out if something is wrong or, why is my computer slow and things like that. It can also help you close programs. So that's what they mean with accounting, which is a interesting choice of words for that. Okay, so from there, they start talking about the different interfaces that you can have between a program and the OS, and the three ones that they basically list are ISA, which is Instruction Set Architecture, and then they have Application Binary Interface. I'm going to abbreviate it, Application Binary Interface. And finally, they have API, which I'm sure you've heard that term before, which, by the way, means Application Programming Interface. And so these are the ways that you connect with a computer as a developer or as a piece of program that you have. The most basic one is the instruction set architecture, and that basically defines the machine language that a computer can follow. Those are your assembly code, basically. And it's basically the boundary between hardware and software, right? Software being the code that you're writing, and hardware being the actual physical devices. So when you call an instruction on something, you're actually telling the physical, the CPU's physical transistors to do a specific task and things like that, right? And so the OS does have additional instructions, machine language instructions, that may not be available to a regular program. And so that's what they mean by instruction set architecture. That's one of the ways that you kind of interface with a computer. You send it instructions and so on, right? Application binary interface is going to define the system call interfaces to the operating system and the hardware resources. And it's available to the user through the instructions that you get, the assembly instructions. It's a little bit abstract, so I'm just going to leave you with that and then let you finish that in 370. The one that's more interesting is the API. So that is actually when you hear the word API, you know, you might hear it like not just in terms of a computer, but like when you're talking like Twitter's API or some sort of website API. And typically, what an API is a program itself or a set of resources that allow you to connect with something. In the specific case of a computer, the API is typically going to give you access to the hardware resources and services available through user instruction set architecture high-level language library calls. So like, if we think of like Python or C++, you know, when you're using IOStream and you say cout hello world, or you're doing printf hello world in C, or just print in Python, or systemln print in Java, or whatever, no, system.println in Java, that's a library call in which you are able to communicate. So that that becomes an assembly sum instructions as part of your ISA, which then, you know, communicates with the OS, and then by telling it, you know, we're trying to output something to the terminal, right? And so the API is basically the list of all of those high-level language libraries that allow you to communicate with the hardware resources. Okay, so again, using an API is going to enable application software to basically access the resources. And the cool thing about it is this: in a high-level language, you know, like cout, hello world, and things like that, is can be easily ported between different systems that support that same API system. So as long as there's a translation from that library call to instruction sets for that architecture, then your program will work in that system, right? The library will work. So if there's support for this library, you know, you don't need to figure out how this will actually reach the terminal and actually reach your screen and print out hello world. You just have to worry and trust that if the specific system where you're building your code supports the IOStream library, then it means it's going to support calls to the screen, right? And so that's the usage in terms of operating systems. The usage in terms of Twitter's API and things like that is basically that there's library functions so you can download stuff. So like in my 202 class, they were doing a Twitter assignment where they were analyzing tweets, right? And so I actually got an account with Twitter with to their API, which gives me a specific login per se. It's a key, and you know, imagine like a very, very long password, and this essentially with that, you know, looking at the documentation of the specific function calls that I can do, I can write specific code that can request from Twitter specific data. And so the code is just Python code, and it's very, very simple code actually. But internally, for Twitter to be able to retrieve the data of certain tweets based on my request is pretty complicated. But again, I don't have to worry about that, you know, traversing the servers of Twitter to be able to get the data I want by doing some weird SQL queries and things like that. Plus, it's also unsafe because I could access things I shouldn't. Instead, they have this nice little front end that basically says, hey, you know, give me tweet data from this user for this time range. And then internally, things are done to support that. And so if Twitter ever updates their system, they can update their API and still have my code working, because internally, even if they have a different system set up for the data, they can update that while still supporting my program that I already wrote to access that. So APIs are a very cool thing that don't just apply to operating systems. So you hear that term used a lot. Okay, so those are going to be sort of your interfaces to connect to a computer. As you can see, they kind of build on top of each other. Really, you know, you can think of the operating system as a resource manager, and because it is, you know, a computer is a set of resources, right? So that you can move data, you can store data, and you can process data. And essentially, the OS is responsible for managing these resources to make your life easier, so that you can request usage of these resources, and the OS can deliver, basically. Okay, it's basically a control mechanism. In general, you can think of the OS as just another program in the computer that is also executed by the processor. And because of this, the processor, you know, I mean, there are some different processors we will talk about, but like in the most basic sense, a processor can only be processing one instruction at a time. Okay, let's just say that. Again, we talk, get multiple cores and things like that. But let's just say we have a single core processor. It can only do one instruction at a time. That does mean that when you're running a program, the OS is not running at the same time. So the OS has to relinquish control and depends on the processor to give it back after running the program. So like, let's say that you have a program, think of like the IAS computer you're building, right? So you put in memory, or the question in the test where you have a bunch of instructions, right? So the OS is going to be like, okay, it's time for this program to run, and so it loads the information and basically makes the program counter and everything point to this thing. At that point, the OS has no control. At this point, it's dangerous in a way, actually, which is why we're going to talk about making this a little bit safer. But then it's just running code. This program is running code, and it hopes that at the end here, there's an instruction that says like, give control back to the OS. Otherwise, like, well, if something happens in the middle of this code and the program just loops forever because you just coded really badly and there's now an infinite loop in here, well, the OS can't jump in at that point, so it's GG. Your computer is basically locked forever until you turn it off. And so, that is something that is kind of risky, but happens because the OS can't interfere there because, again, the processor is just processing stuff. It's processing one thing at a time, and the OS has to give away control. And so we're going to talk about ways to avoid this from being an actual problem. Okay? So, yes. Before that, let's talk about, here. This is a useful term that we should know. Kernel. So kernel is the term that they will talk about again in 370. I mean, they're literally going to talk about pretty much everything I talk about today in 370. But kernel or nucleus, which nucleus I don't really use. I've seen kernel used a lot. It contains the most frequently used functions in the OS. And at a given time, other portions of the OS currently in use. And it's basically like the most lowest possible thing that you could have running in a computer, because it's the most mission critical thing, I suppose. So it's just good to know that word. But anyways, let's talk about the different sort of types of operating systems and their development through history. Okay, so there's two sort of main operating systems that kind of came up, and those were basically the interactive system and the batch system. In the interactive system, the user base interacted directly with the computer and would request the execution of a job, and you can think of a job as a little program to perform something. The user, depending on what it is that you're running, would communicate with the computer during the execution of the job. So like if you request information and things like that. And this is kind of what you can think of as like an interactive program per se. However, the opposite of that is going to be a batch system in which you basically just write what your program is going to do and then, feed it to the computer. And then once it's done, the results are printed out and there's no interaction with the program. Now, you might ask, that limits me in what I can do. Well, yes, but here's the thing. With the interactive system, you got to load the program, run it, and when it's done, you got to actually figure out that it's done and then feed it some other program. With the batch system, if it doesn't require any user input, then it doesn't require any sort of monitoring, and you can just feed it a bunch of programs and basically batch them all together, which is where the name comes from, and be able to process things a little bit quicker. So like think about it from like a grading standpoint of view, in the programming class like 202 or 302 or 135, if you write a program that requires a lot of input, the TA has to manually put testing your program with his input, or what can he do? Well, he can use Linux redirection or something like that and just have a script that runs not just your program, but all other programs, and then saves all the output of each of them, and then he can go ahead and look at that as a batch and figure out which program did good or bad. So these are different systems, and batch system is not really, even the book says it's not really kind of used nowadays. But there is one important thing about it to understand from it, and that is that a batch system requires something known as a monitor, or there's another name for it in the book, resident monitor as well. But let's talk about just a monitor in the basic sense. So, you know, again, the reason why you want to use batching is because you want to basically improve utilization, because you want to be able to feed multiple programs quicker and not have that delay. Because if you think about back to like computers from like the early computers from the 40s and the 50s, those computers like had no operating system. You know, it was just a processor, and you would just feed it data, and then it would compute the data, and then they would return to you by printing something out or displaying some lights or giving some hole punch cards or something like that. And so if you wanted to run a program, you know, you basically would just go up to the computer and feed the information by a punch card or something, and then it runs, and then it comes back to you and it says it's done, right? But you have to be actively controlling it. And if your program is messed up, if the thing freezes halfway, then you got to basically unplug it and plug it back in and reset it and all these things, right? On the batch side, it's cool because you can preset everything to run it, and then when it's finished, it feeds the next one. But there needs to be a way to control when one program finishes to feed in the next one. And that's where the monitor is coming in. So the monitor is basically that the user no longer has direct access to the processor, okay? So before, you have direct access to what you're feeding it, like literally what it is you're feeding it, the zeros and ones. Whereas with the monitor, the user no longer has direct access, okay? So the user has no direct access. There we go. That makes grammatical sense. And so in this case, you basically submit the jobs or punch cards back in the day, and then there has to be a way for the computer to keep track of when a program is running, so that when it finishes, it basically knows that it's done, and it can go ahead and run the next one in the batch, right? But that's trickier than it sounds, you know, because like, how does it monitor that? Well, like, that is a program of its own that needs to be running. So like, are you gonna have a separate computer that is monitoring the first computer, or like, can you do it in the same computer? So things become pretty tricky with that. And so essentially, what you end up doing for that is when you're feeding the program in a tape or whatever, it ends up having this structure. It has the user's program area down here. That's the program that you're running. And then somewhere there's a boundary, which is where it ends. And then you need also to have the monitor stuff. And the monitor can include things such as like the sequencing of the jobs. So if you think of this as like as the memory layout, okay? So this is the main memory of the computer. So somewhere in memory you have the area for the user programs, and it might be more than one. You know, if you're gonna run multiple ones, but assuming you have the space, otherwise you have to load one at a time. But in here, you need to have a job sequencer so you know what's gonna go next. You need to have a control language interpreter. You need to have drivers, so drivers are ways to communicate with hardware, so to communicate with the I/O devices and things like that. And you need to have some sort of interrupt processing so that you can stop programs if you need to ahead of time, or pause them, or things like that. So let's actually talk about some of the challenges involved with this. The biggest one is actually going to be, how do you schedule these programs, right? Like how you sequence them together. And if it's something like an interactive system where you're just feeding one program at a time, that can literally be done with a sign-up sheet. You literally post outside the door, and then you go in there and you reserve when you want to use the big supercomputer that's like amazing because it's like 1 kilobyte of data per hour or something, But hey, it's the 40s or whatever, and so you go in there in the sign-up sheet and you check the time. Maybe there's a slot per half an hour or slot per hour. And then you sign up your name there, and you're like, okay, I want to use the computer from 4 to 5 p.m. on this day. And then you come back at that time, and you go in the room, and you run your program, and hopefully it finishes before 5, so that then you can take your little tape out when you get the output back, and then you go and you analyze this, and hopefully your program actually was correct, because otherwise you're gonna have to schedule another day to come back and run the program again, right? So so much for trying to see if the code is correct in the first go. You want to make sure it's really, really good, because time is very valuable, right? There's two sort of issues with this. Issue one is, suppose that your program, it turns out to take longer than expected, and it's actually going to take about 1 hour and 10 minutes. But then 5 p.m. comes along, and then the guy that's supposed to come in at 5 is like, yo, it's my time to use it, and my time is limited because I got an hour or two, and my program needs like 55 minutes to run. And now he's like, I'm sorry, but like you're hogging the computer after your time, so you know he just kicks you out of the room, and now or you get in a fight, and you know eventually bad things happen, right? So more than likely your program is going to have to be forced to stop before it actually finished running the calculation that you wanted to do, and you know that sucks. So that's kind of a problem. The other problem is if you finish at 4:30 instead of 5, because you know you were like, or let's say this. After you got kicked out, the day after, you scheduled 2 hours because you were like, you know, I'm not going to get kicked out again. So like, to be safe, I'm scheduling 2 hours. And then your program does indeed take over an hour. So you're like, whew, I'm glad I scheduled 2 hours. It takes an hour and 15 minutes. And you're like, well, yay, I'm done. And then you leave. But guess what? Now you have 45 minutes where the computer is idle because you basically took, you know, you scheduled 2 hours, but you only really needed 1 hour and 15. So there's wasted time if a user finishes early or program finishes early. So you need to have some form of scheduling and that can handle this, you know, in advance. And so that was basically the problem with scheduling with the early computers that were like interactive, right? Also, there's setup time involved, so you have to load the data. Also, the computers back in the day this is something that we take for granted now, but when we turn the computer on, it has the operating system loaded. But you know, in the early 90s, in fact, the first computer that I had, but I was a baby back then, was a computer where you actually had to load in the operating system into the computer after you turn it on, because it didn't have it in it. Every time you turn the computer on, you have to load in the OS, and that's one of the first things that you do. And then once you load in the OS, you know, MS-DOS or whatever, then you can actually load in any program that you want to run. That takes time, right? Unless you leave the computer running between different people, that takes time. But even so, you have to load in the program that you want to run as well. So you have that in some sort of external drive or something, and then you or tape in this case, like punch cards or something, and you got to go in there and you got to load the compiler, you got to load the program. Then you got to compile the program, you got to link it, load it in, and load in anything else that needs to be loaded if you're using some other external resource, and then actually run the program. And that takes a lot of time. And that's how it used to be back in the day for big computers. But even in personal computers, you have to load an OS every time you turn the computer on. So that's one thing that we take for granted nowadays, actually. So yeah. Basically, that was the situation. So from there, what are other things that we want the operating system to have? You know, before we talk about multi-programming. Actually, hold on. Let me go in the order of the book. What is next here? Okay. Cool. All right. So multitasking is next. So never mind. Let's talk about multitasking first. Okay. So, because I kind of want to go in the order of the book, otherwise I'll get sidetracked. So, okay. So, you know, batch systems are great and all, but you know, they're not very interactive. So we kind of want to have a mixture of interactive, but also be able to process things in batch. But here's the thing: even when you're processing something in batch, you're doing one at a time. Okay. Now, if you think about like a general program, you know. The general program is going to have code that is running, you know, computations that are happening in your CPU. And then there's going to be probably some sort of I/O involved to read in information from the user or print things onto the terminal. And then there's probably going to be more computation based on that I/O. You know, and that's a very important thing to say, that this is based on the I/O. You know, because especially if this is like I more than O, then you definitely need the information. Like, you know, say you're doing like declaring some variables here. Then you're actually reading in information into those variables, and then you're doing math with those variables, right? And so you can't do this line of code until you've read this line of code, which this requires input from the user. So you can't skip ahead, right? You gotta wait for that to happen. And so on the other hand, you know, with the output, there's a little more flexibility, because if you have somewhere here another IO, but this is simply C out Y, you know, this, and then down here you have other code that doesn't, you know, it's just whatever. It doesn't matter whether this prints out here, especially because if you had other C out IO commands here, so like if there's more IO back here, you know, then sure, maybe you want this to print out before this because it came in order, or maybe you don't care. But either way, you can run this part of the code because it's output related and there's no input involved. Okay, so the O is more flexible than the I. So let's focus on the I for now. In this situation, you definitely have to wait for this code to run before you can continue running the program. So in either system that I talked about with the old system with batch or interactive, you have to wait for this to happen. And we know from our discussions some days ago that I/O is one of the slowest parts of the system. And that's because the devices can be slow, communicating with them can be slow. I/O can also include a hard drive, and we know that access seek time, you know, latency and all those things. It takes time to actually get information from I/O devices or to communicate with them in general. And so, you know, at a single time, there's a lot of programs running on a computer. And even if you can't think of that, think of the basic example of, you know, again, the two guys that are trying to use the computer. Couldn't we take advantage of the CPU? Because right now it's just idle, waiting for this to happen. You know, interrupts are going to be useless in this case because you can't run this code. You know, you can't run that code until you get this. So this program is basically halted until the I/O finishes. However, you know, couldn't you share the processor during this time so that another program could run? You know, somebody else wants to use a computer. Couldn't they use it during that time? You know, and run pieces of their code while that's waiting, and then when that's done, then sure, okay, you have priority, so then they can take a pause and you can keep going. There's no reason to just leave the I/O idling. And so this is the idea of how multitasking or multi-programming came into appearance. Multitasking or multi-programming. And so what does that require? The idea of doing that is like, okay, if we have two processes, you know, there's a process that is going to be running here, and then there's an I/O where it has to wait for it because it's like an input, and then maybe there's some more running, and then there's some I/O, but like maybe that one is output. So it's I/O, but it doesn't have to wait. But okay. And then there's more code running, and then maybe there's one I/O where it does have to wait because there's more input, and then there's more code, okay? And then there's another program, let's just say the easy term, where that one there's just literally a big chunk of running, and then there's finally some I/O at the end for output, okay? And that's the whole program, okay? So we're gonna call this process 1, and we're gonna call this process 2, okay? So process 1, you know, well, if process 2 would run first, then it would be very efficient. They would finish here and then, you know, waits for this and then it's done, right? But let's just say that process 1 is going to run first, okay? So process 1 starts running. So the green means that it has run that much. And then eventually it gets to the I/O part, okay? So there's some code here happening to communicate with the OS to send the I/O request. So I guess we can put that on the color here. That's the gaps in between. And then at that point, you know, it's just waiting. During this wait time, normally you'd be waiting all of this time, and then eventually you get an interrupt saying, hey, we're done. And this you're like, thank God, finally. And then you keep running, right? Okay, well, what about this? We can go ahead and run part of process 2 in that time period. So we can go ahead, here, maybe I'll shrink this so I can have more width to this. So let me go ahead and shrink this out. Oh, come on. There we go. Okay, we're gonna put it like that. So what we're gonna do is we are gonna go ahead and run part of process 2 in there, because why not? The CPU is one of the most valuable resources that we have, and it's not doing anything. It's just being lazy, and you can't afford it to be lazy. So while this process is waiting, we're going to go ahead and have this process run. At least that much. Because then we get the interrupt that this IO process has been finished. At which point we can say, okay, cool. You know, we were being a good neighbor and letting you use this while we were waiting, but since we are first, we are going to keep going now. So then they tell process 2 to wait, they save that information, and then process 1 can keep going. And then there's some IO requests, but this IO is not mission critical because it's output, so maybe it can happen, but you don't need to wait for it. So while that is happening, you know, you kind of put it to the side. There's a little bit of overlap there because there is some time that you have to communicate to the OS that there's an IO operation about to happen, but that can happen in the background while you're still running, right? You don't need to wait for that one. Especially unless you care about the order of things printing out or something, or even if you did, it's only until the second IO where you would actually have to wait, right? But in this case, there's no second one, so that can just be going there while you're running the code. But then you finally do get to an IO that requires you to wait. That's okay, no problem. What we can do is we can actually take the remainder of what we have in the second process and run it while we're waiting. So let's go ahead and do that. The thickness of my... No, never mind. It's because I shrank it. Okay. So how do I split this? This is tricky here. Here, let's erase that. Okay, yeah. That kind of works. So let's go ahead and run the remainder of this right here while we're waiting. Okay? So while the waiting is happening here, you're going to go ahead and run part of process 2. Eventually, yet again, you get an interrupt saying like, hey, the IO thing is done, and you're like, yay, okay, process 2, my turn again. So like, okay, thanks, you know, I'll give you the CPU when I'm done. I'm almost done, I promise, but now I got to finish my thing. And then process 2 is like, yeah, sure. I mean, after all, it's better than me just waiting for you to do the whole IOs, you know. You can start getting some work done ahead of time. And then you run this and finally you're done, assuming that you also have this one done. Otherwise, you got to wait for this to finish. But, you know, that finished pretty quickly as we see there, so that's okay. So then you're done with this, and now you're fully done here. And so now, for the remainder of the time, you can run the remainder of process 2. So then now it's this, you're like, it's all yours, process 2. And so process 2 can run it. And of course, at this point, there is some IO, but you know, there's nobody else needing to use the CPU, so that's fine if you're idling it here because there's nobody else. If somebody else came, you know, if there's process 3, then he could start using it right here. But there is nobody else, so we're good. So as we can see, this is much better than having to basically run the equivalent, which would have been process 1 and then process 2, which probably around there. So we essentially saved this much of time here. We saved that much and that much, which we would have had to have added here. Okay, so that is the amount of time that we saved by basically not making the CPU be wasted by just idling there. Okay, because that's fast. The stuff that's slow is the IO, but the CPU is fast. So we want to make sure we maximize it. You know, we want to exploit it to the max here. And so this is the idea of multitasking. But this sounds cool in theory. You know, it's like, oh, nice. But like, if I told you, hey, you got to add this to your IIS assignment, and then you start adding it, you'd realize that this actually becomes rather complicated rather fast. So, yeah. Because here's the thing. If you think back at the IIS example, you know, there's a couple of... So first you got the memory for like for a single process, you know. You have your main memory that is running the instructions, and then you got your registers like your program counter, your instruction register, and then your accumulator, which, you know, in x86 and things like that, there's like a billion different other registers. But the point is that even in the most basic example, you have this data, right? And so when you're running program A or process A, sorry, has this data. So if, you know, you want to take advantage of the wait and throw in process 2, you need to feed in processes 2's data in here, which means that the program counter needs to be changed, the instruction register needs to be changed, and potentially what's in the accumulator needs to be changed. But you can't lose that data, because if you lose it, then you can't restart process 1. So you're going to have to copy all of this data somewhere into memory. Well, this is already in memory, but you want to copy all the register data into memory, back it up somewhere in main memory, and then load in process 2, which is going to have its own program counter. Maybe the first time there's nothing there except the program counter. There's nothing in the instruction register or accumulator. But by the time that you finish this first wait, and then you're going to interrupt process 2 again to go back to process 1, then you got to do the same thing for process 2, because now at this time process 2 is going to have its own information in the instruction register, in the accumulator, and so on. So now you're going to have to back those up into memory as well, and then you're going to have to reload processes 1 stuff back in there, and then you can keep running it. And of course, the process of loading things into memory and back takes time of its own. Now the question is the time it takes to basically save all that information into memory, load another process's information, and then run that code, and then when you get done, load back up that process and load back the original process, is the time it takes to do that process. So here, let me write the process down. So basically step 1, so we'll say step 1 is going to be, there's some IO, and because there's some IO, what you're going to do is you're going to back up all registers, let's say, okay? All registers. That's step 1. Step 2 is basically load. If it's a new program, you just load it in, but if it's something that you've already run before, you're going to have to load all registers of process 2, backup all registers of process 1. Okay? Then eventually, IO of process 1. IO of process 1 is done. And here IO of process 1 starts. So step 1, IO of process 1 starts, which means that the CPU would be idle while you're waiting. So at that point, you back up process 1, you load up process 2, and then I guess there's technically this step 4 is you run process 2. At some point, the IO from process 1 says it's done, at which point you stop. I guess write the word stop in here as well. Stop and back up all registers of process 2. Save them in memory and whatnot, and then go ahead and load all registers of process 1, and I suppose at that point, run it, which I guess is the same thing. Well, I guess I did put it in a separate instruction, so I'll put it here as well. So 8, run process 1. So there's a lot of memory accessing, right? And memory accessing can be slow. So the question is doing all of this worth it for being able to save that much processing time? And the answer is, it really depends how long that wait is. If that wait is like 10 days, heck yes, it's worth it. If it's 10 seconds, I say it's still worth it. If it's 1 millisecond, it might or may not be worth it, because if it takes you 1 millisecond to do the IO, the IO, if it takes you 1 millisecond to do the IO, but it takes you 2 milliseconds to do this whole loading and storing, then it's not worth it, right? So there's, and then you got to throw in the cache concept in there as well and whatnot. So it's a complicated process that there's definitely a pro and a con to it. But in general, if you do working your cache correctly, you can load and store these programs back and forth very quickly, to the point that it's usually worth it. It's usually worth it to do this. Okay, so that's basically the concept of multitasking, and I'm going to talk more in detail about this in a second here. But since I am going in the order of the book, I do want to talk about 4 desirable hardware features. Why is this in this order? That just feels very random. But we'll talk about it, I guess. So I guess these are 4 other desirable features that we want to have. I see now what they mean. So, okay, if we're going to be implementing this system here with the context switching, I believe that's actually the official term for that. It just came to my head. I think that's what it's called, context switching. Again, they will definitely talk about this in 370 in better detail. I do hope I get to teach that class one day, because I do want to refresh this material. And obviously the best way to refresh it if I'm forced to, because I gotta teach it. So yeah. So context switching. Okay. So I believe context switching is the idea of taking one process out and then saving all the registers and everything, and then loading another one in and putting everything in. Okay. So if we're going to do context switching, there are some special additional hardware features that we want to have to achieve that and to make it better in general. Okay. So those desirable hardware features can be summarized to 4 things. We definitely want memory protection. I'll talk about them in a second. Let me write them down first. So we want timer, privilege, instructions, and interrupts. And most of these might be self-explanatory, but let's start with memory protection, okay? So if we got multiple programs running, and again, the monitor is going to be what controls them. Again, another term for monitor, or more defined term, is resource monitor, I think. Resident monitor. So resident monitor is going to be the utilities and common functions that are loaded as a subroutine to the user program at the beginning of any job that requires them. So basically, your monitor is going to be what does the context switching in a way. So that monitor, it needs to basically, that monitor itself is instructions as well. It's a program. So that has to be held in memory, and you don't want it to be accidentally changed by other things, right? So you want to have memory protection so that it doesn't get changed by program 1, process 1, or process 2. In addition to that, you don't want process 1 to mess with process 2's data. You want to have some sort of protection there to limit access to that, as I was talking about earlier. And in the case that there is unauthorized access, you want the monitor to abort the process or the job and print an error message and then move on to the next process. It's not just going to be like, hey, there's an error, I'm going to stop now. No. That guy's like hardcore. There's an error, he tells you there's an error, but then he moves on to work at the next job because he's got a lot of things that he has to do. The list of to-do things is really high. So, yeah. So that is going to be basically what we all know and love as a segmentation fault when you're trying to access memory that you shouldn't, right? And you get the core dump thing. That's just basically the memory protection stopping you from accessing things you shouldn't. So, yep, that's memory protection. The timer is important because suppose right now, obviously, the way that I gave you this example, I was saying like we're running process 1 and process 1 has priority to run before process 2, right? But in the real world, you got a lot of processes that have to run, and they all want to run at the same time, and they all think they're the most important person or process to run. And so the system, the OS, has to basically be like, okay, guys, I know you all want to run. It's like everybody goes to the DMV and they all want to renew their licenses and whatnot. So the OS needs to basically be like, okay, I need to create some form of organization to decide who's going to go first, who's going to go last. And furthermore, because it is important for the computer to kind of keep running, and you will have multiple programs running at a time. You can have like YouTube open, you're watching a video. At the same time, you might be listening to music. At the same time, you might have PowerPoint open. At the same time, your computer is actively monitoring if you are connected to the internet. There's also an audio device that it has to be connected to and check. There's also, here, let me click on the computer and see what is, here, I can open up my task manager and see what's there. For example, in my case, I have a program that is communicating between the iPad and the computer so that it can record. And then I have OBS Studio. And then I have my notes up in there. I have PowerPoint open. I have antivirus is running. Unfortunately, I have the Adobe Acrobat Update Service, which I hate that. I'm going to uninstall it again. I also have Cortana apparently running. I have Racer's keyboard and mouse thing running. I have Dropbox running, which is constantly checking to see if there's new files. And these are all programs that need to be actively running, and they would like to just be running forever, always. So the OS, and there's a lot more. This is just literally hundreds of potential processes that might be one to run at the same time. So the OS wants to give a slice of the CPU to each of these guys, but at the same time, it needs to control how much time they use, because if it lets them if you just give them control, then they're not going to get it back, and then they're going to hog it, and the computer's going to slow down. And think of it like a movie. A movie, when you're watching a movie in the movie theater, well, back in the day, I suppose, it's being projected from a film, and that film is just a bunch of pictures, right? And those pictures are moving in the strip of film at a speed of 24 frames per second, which means that every 1/24th of a second. So here, picture. So film 101, guys. So you got your film here, and in that film there are pictures, right? And they're sort of in this order. And so in here you have a light that is shining upon the picture. So you got like a little light bulb that is shining there, and this is known as the projector. And then down here there's a screen, right? So it's shining light through this picture so that it basically makes it look bigger. Okay? But if you just did that, it would just be a static image. What happens is this thing is moving very fast at a rate of 24 pictures per second, which is frames per second. And so that means that every 1/24th of a second, actually every 1/48th of a second, a picture basically moves, and then for 1/48th of a second, it shines the light. So really, even though there's 24 frames, there's time that, it can't just be every 1/24th, because the process is there's a picture, which needs to actually move to the spot, stop, have it light shine, then close the shutter, then move to the next picture, then turn the shutter on. So the shutter is actually moving at 1/48th of a second, which is done with a little wheel that is spinning, which is why you get rolling shutter effect when you're taking a video. But that's besides the point. The idea here is that the idea of a movie is nothing more than just a bunch of pictures that are continuous, and they imitate, or they give the illusion to the brain of movement, because it's so fast that the brain merges or meshes the pictures into continuous movement. Now, if you slow this down to like 10 frames per second, you start to see stuttering, because you actually start to see the difference between each image. And then the faster you go, the more surreal it looks. That's why TVs or live video, which is usually done at 60 frames per second, or 50, depending on if you're using PAL or the other one, which is NTSC or whatever. No, that's something. Whatever. The higher frame rate is going to make things look more natural, because even though you don't really see it, your brain kind of does detect that there's something weird going on and it's not continuous movement. But eventually you get it fast enough that not even the brain can kind of pick that up. And so that's kind of the same way that the computers are running. You got a bunch of processes, and they're all doing a tiny little bit at a time, but because they're all happening so quickly, it all looks to you as if it's all happening at the same time. It really looks to you like when you're watching YouTube, you're watching an actual moving video, and at the same time, you're listening to music, and those two things are working at the same time. But the reality of thing is that for like 1 nanosecond or a very, very small fraction of time, your CPU is focused on generating the right frequencies for the music to play. And then for the next nanosecond, it is focusing on generating the right pixel colors for the image to play. And then for another nanosecond, it is focusing on checking, or at least sending the request to the Dropbox servers to see if there's new files added. And so it is doing all of these things as, independent of each other, but it's doing them very close to each other, that within 1 second, it's requesting a bunch of these at a time, And to you, it looks like they're all happening at the same time, but they're not. Just like with the moving picture, they're all happening one individually, but they're all happening close to each other so quickly that it all seems continuous to you. And it's beautiful, actually, when you think about it, because it just seems like we're able to be running all these programs at the same time, but in reality, only one program is being run at this. If you have multi-cores, then you can actually have 2 programs running at the same time. But even if you had like a 20-core, multi-threaded computer that can be running you got like 40 threads and whatnot, if you're still running 50 programs, then there is going to be some sort of sharing going on. And so ideally, you hope that programs are, the Dropbox is only going to do this really fast, and then it's going to be like, don't worry, I'll just take 1 second to do this, don't worry, But it's not true. They're going to take a long time, because they want to be constantly checking. So the OS needs to do a timer where it's only going to give a small fraction of time in the nanosecond amount to each process to run before switching it over. Because if it's too long, then things slow down, and again, it's kind of like slowing down your picture. You know, you start to see the stutter. You start to see when like it's focusing on this, and that's not good. And if it's too fast, then nobody gets things done, and most of the time is dedicated on context switching versus actually letting them do their job. So the timer is important, but you gotta kind of, it's a careful balance, okay? So that's the other desirable hardware features that you want to have. You know, very long story for that. The third one that we have is privileged instructions. So there's special instructions that only the monitor can execute, and if the processor encounters such an instruction being run by a normal user, like a program, then that's an error. An example of that could be I/O instructions. So like, you know, the monitor or the OS is going to retain control of the I/O devices, and like I said, it's the middleman. You know, the middleman wants you to talk to him if you want to talk to the I/O device. If you want to talk to the hard drive, you talk to me first. You don't go straight to the hard drive. You talk to me. If I catch you going straight to the hard drive and cutting me out, then I'm gonna stop you, and I'm gonna generate an error and interrupt you. So yeah, it's like mafia level here. Okay. So and there's some for a reason for that, because if you let them access directly, they can mess things up. You know, you can create chaos. The whole point of the OS is to organize things so that things run smoothly. You know, it's not there to make your life hard. It's actually there to complete the opposite, to make it easy. Okay, so yeah, you know, they're trying to avoid chaos. Finally, you want to have the ability to do interrupts, which we've talked about in the past, right? It gives you more flexibility to be able to relinquish control to a program and then actually be able to regain it later on, right? So that once you get the program access to the processor, you can actually take it back, especially if it crashes or something. And so, yeah, that's pretty much the desirable features. So now things get a little bit more interesting here, because we talk about scheduling. So scheduling is going to be a big topic in 370. You will talk about different kind of schedulers. So I'm just going to give you a very brief introduction about that. But as you saw, you know, we have Dropbox and we have all the other ones that I said, Chrome and YouTube, all these things running at the same time. Well, YouTube isn't Chrome, but whatever. We're playing Warzone at the same time, okay? So ultimately, you got to figure out who's going first. You know, I mean, yes, you're going to give them all a piece of this, a time slice. You're going to give a small amount of time, but you got to figure out who gets what. And also, there might be situations where you have things of higher priority that you want to run. You know, well, you can actually set it in Windows, certain programs to run with higher priority. But in general, there are things that you want to have higher priority. For example, I/O is very slow. I've been saying that all day, right? I/O is slow, I/O is slow, I/O is slow. And within I/O, they're slower than other ones. Like there's I/O like input/output, and there's also I/O to like a disk drive, and then there's also like communication on the internet and things like that, right? So here's the thing. If you send an I/O request and then you get something back from the I/O, then you definitely want to process that quickly, because you might already have 10 of the things that you want to send to the same I/O device. So then you're like, yeah, let me process this, because then I'm going to send you something else to do, because you're so slow that I want to make sure that you're really busy all the time. You know, you don't want to waste time there, because again, the slowest thing is the I/O device. You know, if you have a business, right, and you have one part of the business that's the slowest, maybe sending stuff, delivering stuff is the slowest part. You know, so if you have a new delivery driver who just arrived, you want to send him out as quickly as possible. So then you want to fill up his truck and then send him out. You want to prioritize that over anything else, because it's really slow. So you don't ever want to waste time there, because you're always waiting for these delivery drivers to arrive. So when one is actually there, you want to take advantage of that to the max. And so within scheduling, there is not just a matter of organizing who goes first and then actually giving them a fair amount of usage time in the CPU, but also to have priorities as well. So certain things can jump the queue basically. And there's also different layers of scheduling to be able to set up this system. So before I talk about the different layers, let me just talk about one basic way of doing scheduling, and it's with a queue. But not just any kind of queue, but what we called sort of a circular queue, or a round robin. Round robin is like, imagine you're playing a game of cards and you're just passing out cards. And so you pass them out in a circular manner to each person, right? So, you know, you pass a card to here, then you pass a card here, here, and then you're passing the second card. So you go here, 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 and so on. I think I'm gonna, no, I didn't mess it up. So yeah, so this is you basically dealing cards on the table, a round table. That's kind of how your round robin works. There are more than one way of doing scheduling. You will get to not just learn how to do these scheduling algorithms, but you'll probably code them as programming assignments in 370. So good luck with that. Have fun. It's actually kind of cool. So yeah, essentially, again, this is an example of a round robin scheduler where you give this guy a little piece of the CPU, and then you go to this guy, and then you go to this guy, and then you go to this guy, and then you go to this guy. But in addition to this, you may want to have a priority queue where something wants to cut in the queue and be able to process that first. And within that, there might be different layers of priority. So scheduling can become a very interesting topic to explore, and that's why they dedicate at least quite a while of the time of 370 to it. I'm trying to remember from my own 370 sort of knowledge of what we did with that. But yeah, definitely about a month of time I would say that they spent with scheduling, and also with electing stuff. I remember talking about like election algorithms too, but that's unrelated to that. But yeah. Anyways, sorry, nostalgia trip there. How many years ago did I take that? That's a long time ago. Okay, so yeah, moving on. Scheduling, that's all I'll say about scheduling. So if you want to find a lot more information, look at like round robin scheduling, and just look in general. Google like CPU scheduling algorithms, and I'm sure you'll find like a dozen that to talk about different ways of figuring this problem out. It's a complicated problem, by the way. It's not something easy because you want to avoid starvation, which is where you're not giving enough time to a process, but at the same time, you want to make sure that everybody gets a fair share and that things get done quickly. Maximize the usage and things like that. So it's an interesting problem. So within that, there's different sort of types of scheduling that I do want to talk about within the CPU. I won't talk about all of them, but I will talk about some of them, and that is going to be. Here, I have them here. So there is long-term scheduling. So scheduling types, not scheduling algorithms. Again, those we're not talking about. But within scheduling types, there's long. So the way we're going to accomplish doing this whole multitasking thing is by having sort of different queues. And the best way to think about this is like Disneyland. When you go to Disneyland, some of the rides have most of the rides have a form of a line to get in the ride because there's more people that want to use a ride than there are seats in the ride at one time. And you want to be fair about it. So the person that's been waiting the longest is hopefully the person that's going to get served next. So because of that, they can't just make one big massive line, because of the way that the rides work. Like, you can't, you could in theory. Some rides do that, like Pirates of the Caribbean does that. It's just one big massive line. But if you go to a ride like the Guardians of the Galaxy or the Hollywood Tower of Terror, what ends up happening is you usually have a line outside, the ride, and then eventually you go inside, and you might need to change floors or use a stair. And having lines of stairs is kind of risky, I guess, because if somebody falls, they just kill like 10 people. So there might be an elevator, or you might want the line there to end, and then once the stairs clear out, like Indiana Jones has this too, then you let more people flow. And so, you could think of this as one independent line, and then inside you have another line. But you only let people into this line when it kind of empties out, and then you fill it up again. And then maybe there's a third layer of lines that one is going to be the individual line to get into seats in the rides of the car. So like this you will see in like Space Mountain or Indiana Jones or pretty much any seat-based ride where like there's like little places for you to stand so that when the next vehicle arrives, then you just they go out, egress, and then you enter, and then this empties out, so you fill it up again. So it's sort of a lineception. You got a bunch of lines all over the place to kind of to organize things to be as efficient as possible, because you want this ideally, the whole process of this is to maximize how quickly you can empty people and fill people in the car and move on, right? And also make it safe. And I bet you now things are like 10 times harder with the COVID-19 stuff. So poor Disneyland. But I'm sure they'll handle. I hope they do. I mean, that'd be tragedy if they like shut down forever or something. So yeah. So same thing is gonna apply with CPU. You know, CPU Disneyland land, CPU land. Okay. We have long-term scheduling. We have medium-term scheduling, short-term, and I/O scheduling. Long-term scheduling is the most basic sense. So like, you know, you execute, you do ./a.out, you know, you run a program in your computer, and what's going to happen there is it's going to add it to a pool of like processes that are going to be executed. So it's adding it to its to-do list per se, okay? So it's like, okay, this guy wants to run this program. I'm not ready to run it. I'm just going to put it in the to-do list, okay? At some point in time, you know, there's other stuff ahead of it. It's going to, or depending on priority, if it's an important thing, it might immediately jump that line. But at some point in time, it's going to go on into the medium-term scheduling. The medium-term scheduling is when it's actually, the OS is actually going to load the program into main memory. Because remember, you know, in your regular computer, you got your hard drive, then you got your main memory, and then you got different layers of cache, and then you got your CPU registers, okay? And so at some point in time, you say, I want to run this program, which is actually stored in the hard drive. So it's going to request to load it to main memory once there's actually space in main memory. So, you know, the to-do list to load it to main memory, this is long term. And then the medium term is once there's actually a decision to add a piece of the program into main memory. And I'll say a piece because we'll talk that in a second when we talk about paging, that you don't have to load the entire program into main memory. You can load a piece of it. So for now, just go with me that you load a piece of the program or a full thing if you really want to, okay? But the process of doing that, you know, now it's like, you know, it took the elevator and it's getting closer to the front of the line. So we got to get ready because like what we don't want is this. In this system here, you know, again, I said this whole process takes time of loading things and switching context and all of that, right? Just like in Disneyland, imagine that like in this line, all of a sudden they said like, okay, go in C2, and you're like, oh crap, okay, let me jump to C2 and get in there because it's my turn. You don't want that. You want to slowly get everybody ready. So once the time comes for the CPU, then bam, they're ready to go and they're ready to get in fast, right? And the same thing here. If you don't have something in the cache ready to go, it's going to take a lot of time because you have the cache misses, right? And or even if you have a main memory miss, imagine that like something in the hard drive is like, okay, we're ready for you, proceed to CPU, and it's like, oh crap, it's gonna take like 1 millisecond just to get the information here, and then like a couple of more nanoseconds to get it there, or picoseconds to get it there. And so it's bad, right? So we wanna prepare it. And so that medium-term scheduling is basically when you're loading it in main memory as the time comes closer for its time in the CPU, okay? Finally, we have the short-term scheduling. When you get into that line, so like once you've waited long enough, I suppose, it's basically the decision as to which available process will execute by the processor. So that is where the processor is like, okay, your time has come, or it's about to come. You know, you're like next in the queue, or maybe there's five in front of you before I'm actually gonna get you. You're gonna get to use the CPU. That's when you're gonna probably be loaded into the caches. You know, and you're ready to go right there. You're like fully active and ready to go. So that when those 5 people go in front of you, then you're next. You can be ready to hop right in and start running because your time starts when the CPU says, I'm ready for you. And if you're not ready, you're wasting time. And if your time expires and you still haven't loaded in because you weren't ready, then too bad. You've lost your chance here. So it's like the Disneyland cars. If you don't get in the car in time, the car leaves without you, and then you gotta wait for the next one, kind of thing. I mean, I don't know if that's how they actually would do that, but they probably would pause the ride. I don't know, but yeah, that's kind of the thing. Okay, it's like in the Haunted Mansion where they have the people mover thing next to the cars, and if you don't get in the car, then you just go for the next one. So yeah. Essentially, when you're in a short-term queue, your time has come or it's about to come. Okay, and so bam, you get executed. Okay, and so then your time expires. What happens then? You don't just go to the long-term queue at that point. What you're gonna do is you're probably gonna go to the short-term queue, and then you're going to chill there until your time comes again to run again. You know, if you haven't finished at that point, and you'll basically be there. Now it's possible that you may get relegated to the medium term queue or whatever scheduling algorithm you're using. I'm just saying queue because it's the most basic thing, but round robin, you may get relegated to that if there's higher priority things that need to run. In which case, you know, that's okay. When the time comes again closer for you to actually run, then you'll be moved back into the short-term queue. Finally, there's the I/O scheduling, which is its own set of queues per se, and that's basically what I've been saying all along, is that the decision to figure out which I/O requests are going to be handled first and which are going to be handled later is going to be handled by the I/O device directly, or by the OS, you know, who's sending what to what. So like if there's a higher priority I/O thing to do, such as if you're receiving communication from the internet, you want to prioritize that information and so on. So that it has its own sort of scheduling to figure out to maximize the usage of the CPU. Okay, and a picture for the short-term scheduling, which is the one that is more important. And again, this you will. In fact, when I was looking at this picture in the book, I got flashbacks from 370. So. I'll go ahead and draw that picture here. This picture will become more complicated as you traverse 370 though. I remember that much. It's like you add more circles to this thing. So let me go ahead and fill it up first. And I am doing a bit of a disservice to this because, I mean, it's an entire class that you're trying to cover in one day. So there's so much stuff that I'm cutting from this, but, you know, it's not the focus of this class. The focus of this class is the entire computer, not just the hard drive. Sorry, not just the OS, right? It's more of the introduction, and then you will learn about this stuff. You have to know a little bit about everything before you can focus on the OS, which is what I think the main purpose of this class is, to kind of get you to kind of make you aware of this and also to prepare you a little bit for this. So I hope that this lecture today prepares you a little bit for 370. But by no means is it supposed to be like when you get there you're like, oh, I didn't learn this. No, I mean that's their job to teach it to you. So they should hopefully go over everything I talked today in 370. Not get a refund. So yeah, okay, and in far more detail too. So here we have the sort of what they consider the process states. Okay, so this is a process state diagram. So like, or kind of like your instruction cycle. This is your process state. I guess you can also call it process state cycle too. So we'll just say process state without the word diagram in front of it. The term state is used because it connotes that certain information exists that defines the status at that point. Okay. At a minimum, are 5 defined states for a process. And that's what the book says because, again, there will be more sort of in-between states that you will add as you learn more things. Just like when you learn about instruction cycle, and then you made it more complicated because we added interrupts, right? And that kind of situation. And it will become more complicated, too, when we talk about pipelining in detail. I hope we do. That's the last big topic that I want to cover before the end of the summer. So, yes. Hopefully next week is that. So yeah, so what are these? The first one is going to be when you basically execute your program, which is new. That's going to be a program is admitted into the high-level scheduler, but it's not ready to execute. The OS is basically initializing it, and once it's doing that initializing, then it can move it to the ready state. So once it's been kind of initialized, then we're going to go there, okay? And then in the ready state, it's basically the process is ready to execute, and at this point, it's just waiting for access into the processor. At this time, it's probably when it has been moved to memory, okay? So for you to be admitted and go ready, more than likely you need to be at least moved into main memory so that things are not super slow. At some point in time, the dispatcher, which is the name of the short-term scheduler, is going to be the one that actually makes the decision that when your turn is to go. And that dispatcher is going to be like, okay, you're next. And so in that case, you're going to go into the CPU and you're going to get your time share of that, time slice of the CPU. Okay? At that time, hopefully you finish. And if you do, then if you either you finish at the end of your time slice or you finish before you finish your time slice, then you get released and then the program exits and you're happy, right? More than likely though, the time slices that you're going to get are so small that you will not finish with the first one that you get. At which point, your time will expire, and then the dispatcher is going to be like, okay, get out of there, next person's job. And so at that point, you're going to halt execution. The context of all of your registers that I was talking about here is going to be saved in main memory. And then you're going to be sort of put in this sort of waiting state. Okay? Another situation where you might be put into the waiting state is if you have an IO request, like I said, at which point there's no point in you just idling in the CPU waiting for the IO request. They're just going to be like, oh, you got an IO request? Then get out of there and let somebody else work while you wait for your thing. You know, you can wait in the waiting room, but don't wait here while we're working, right? And so you get sent here and you're sort of waiting, right? At which point, at some time, there is going to be that interrupt saying that the IO is finished. And then, once it's finished, you're not going to go right into the CPU. You don't get that luxury. You're going to go into the ready queue. And you're going to go into the dispatcher's queue, and you're going to be like, hey, my IO finished. Can I go back in? And it's like, yeah, sure, you will at some point, but not now. Go in line, and then I'll get to you eventually. And depending on your priority, you know, you might actually be dealt with next, or you might just be put into the list and then have to wait. So this little round robin queue here probably is you're going to go in there and you're going to wait until your turn comes again. And then you might go back into the running, at which point two things can happen. Yet again, your time will may expire, at which point, by the way, if it does expire, I guess I didn't say this, but this is what the timeout thing is for. So technically, I guess if you time out without an IO, you go back into the ready queue immediately. Yes. I might have said that wrong earlier. If your time runs out, it's called a timeout, and you just go back to the ready queue for another slice, okay? If you do have an IO thing, that's when you go into the block thing, okay? That's when you go here. Only for the IO or some sort of external thing where you have to wait, okay? But if you just run out of time, then you go here. So let's say you run for 100 nanoseconds, and then your time expires. And then you go, the dispatcher is like, hey, you're done. Go back to the ready queue and wait for another slice. And so you go back there. So you go to the purple line down here, okay? Blue purple line, like that, okay? The second time you run in there, this time you have an IO thing actually about halfway through your time slice. At which point, then you get kicked out by going into block. You don't go into the ready queue until the IO finishes. When the IO finishes, then you go into the ready queue to run again. Now, if I remember correctly from the 370, if you have a situation where like you were running for like, let's say your time slice is 50 nanoseconds, but you only run 5 nanoseconds before the IO thing, then you have to ask yourself like, hey, that's not fair, you know, like I get 50 nanoseconds, but I didn't use 45 of those. Can I get those the next time I run? You know, and the thing is that it's a dilemma, right? You want to be fair, but if you have IO things, you know, that kind of messes things up in terms of fairness. So you might want to give it a little bit extra time next time, maybe not the 45, but maybe 20 extra, because he really didn't use them last time because of his IO call, and he was nice enough to, well, not nice enough, he was basically forced to give up the CPU while he was waiting for that. So this is all like scheduling algorithms that I have to deal with that you'll get to play with in 370. But I just want to make you aware of that being something to think about, okay? Anyways, when it's finally done, then it's gonna go here and exit, at which point it gets taken out of all the queues. So yeah, that's your basic scheduling 101 for you. The question is, how does this work? How does this whole context switching work? Okay, the way that context switching works is I'm actually gonna switch over because I don't feel like writing all of that, you know. So let me switch over to the my back hurts. I gotta change chairs, but the chairs that I have is no longer sold because of the virus, so that sucks. So I gotta find a new chair. So here is what is known as the process control block. Okay, the process control block, as defined by the book, says for each process in the system, the OS must maintain information indicating the state of the process. So like if it's ready, new, if it's running or blocked, and other information necessary for process execution. For this purpose, each process is represented in the OS by a process control block. Now, what the layman's term definition of this is when you do the context switching and you gotta save all the register and stuff, you can save it into this process control block. In addition to also figuring out whether you're waiting for an IO, whether you're ready to run, whether you're currently running, and so on. So let's talk about these. Identifier is just going to be some sort of process identifier, unique, so that each thing has a name, basically, an ID. The state, again, can be whether like you're running in the CPU right now, or you're ready to run, or you're blocked because you're waiting for an IO call, or you just been created, right? So that state makes it easy for the dispatcher to figure out if he can put you back in, right? Because the active, when the IO call finishes and you want to go back into the ready queue, you can't do that. You can't just jump in there. You gotta turn your little state signal and say you're ready, so that then the dispatcher can actually insert you into the ready queue. So this is complicated. Priority is going to be, again, because as you can guess, some processes need higher priority than other ones, like mission critical things in your computer that can't wait, like communication related or other things that if you don't handle them, you lose them. So that priority, you can think of it like a bigger number is higher priority or a smaller number is higher priority, whatever you want, just some sort of priority system, okay? Program counter, memory pointers, and context data, that's going to be your register stuff that is required when you're running the program. So like in the IS computer, the ones that I was saying, like your accumulator stuff, instruction registers, and your program counter, which basically says when in your program you've been running. So the last instruction that you ran before you got interrupted and so on, that is what is kept there, so that next time you can pick off where you left and not have to restart anything. So you just right where you left. It's like you've never left before. IO status information is if you're waiting for like if you're blocked, and why you're blocked, what IO you're waiting for, and so on. And then the accounting information kind of goes back to the whole resource monitoring, so like what you're using and so on. And the little dots, it means that there's more to it than just that. There's context data is well, we talk about context data, but here in the book it says it's registers in the process while it's executing and so on. Oh yeah, accounting information. The other thing that you want to store there is how much time of the processor you used. That way, like I was saying, suppose that you use the processor 3 times, and each time you were supposed to get 15 nanoseconds, but the last time you did it, you only used 5 of those nanoseconds because then you did an IO call. So you want to keep track of that, because maybe the scheduler might give you a little extra time the next time you run to make up for that time that you lost because of the IO call. So yeah, there's a lot of things that you can keep in this, and it can get pretty complicated, as I said. But I think that's where I'll stop talking about queuing. Yeah, let's move on. So to be continued in 370. Let's talk about memory management now. This one I'll go a little faster through because this is getting pretty long. I have no idea how long this has gone, but yeah, okay. So memory management is 9.3. Is going to, again, kind of extend upon the idea of multitasking and how to handle that. Because, in unit programming, which is where you just run one program, main memory is just divided into 2 parts. You have the OS memory, which is where the resident monitor resides, and you have the part of the program for the memory of the code that you're running, right? So like you have the memory required to run the monitor, and then you have the memory for the program. And that is, of course, split into 2 parts. You got your instruction set, and then you have your data, right? But the point is that this is all stored in memory, main memory, or RAM, or whatever, or caches, or whatever, right? So the thing is, when you have a multi-programming system, you want to make sure they have effective memory management. Because here's the thing, and this is right from the book. If only a few processes are in memory, then for much of the time, all of the processes are going to be waiting for I/O, and the processor will be idle. Thus, memory needs to be allocated efficiently to pack as many processes into memory as possible. What this means is as follows. This system that I drew ahead here is great. You really do save time. But the reality of things is that most programs are going to have I/O. I'd say like 90% of your programs have I/O. Because otherwise, like, why is the program running? Like, what is it doing? If it's not resulting in some sort of output or input, what's it doing, right? So it might be something related to the monitor or things like that. But it needs to be doing something. And so the reality of things is that if you got 10 processes running, you got process 1 has this, and then it has an IO call. And you got process 2, which is kind of the same thing as process 1, where it just runs some code, and then there's some IO. Okay, so what do? You're like, okay, I'm going to be smart about this. I'm going to schedule the processes to kind of overlap with that. Okay, and so you do that. You set it up like this so that all the time that there's IO, you take advantage of that. Ideally, you hope that if you have 4 processes running, that if this one's in IO, this one's in IO, this one's in IO, hopefully before this one gets to an IO, at least this one is done, so then you can schedule that back in. The reality of things is that most of the time that's not going to be always the case. It's going to get a situation where they're all waiting for IO. Like, this guy is still not done, and maybe he just finished, but then this guy's not done by the time that the other ones are waiting. So you're going to have situations where if you got 4 processes, they're all waiting for IO. And so now you're really just stuck, because at that point the CPU is like, well, everybody's waiting, so I guess I'll just chill because there's nobody to process information. And that actually ends up happening, and that's a problem. And so the solution to that is a simple one. If they're all waiting, then feed more processes. If you got more things that you can run, then run them. And so maybe you can put in 20. And then if you have 20, then hopefully all 20 of them can never be waiting for IO. But if they are, then let's feed another 10 in there. And this is great. You can keep feeding. As long as you have things to run, then you can keep feeding them. The problem arises that you have to load the program into main memory. And main memory is a very valuable resource, And if you're running 20 programs, that is a considerable amount of space when we think about modern computing. Because just one program may be using like half the memory potentially. I mean, it really depends. Like if you're running Warzone or running a video game or something like that, or Chrome, they hog a lot of memory. And so you want to run like 3 instances of Warzone or 3 tabs of Chrome, well, that's, or 20 of them, eventually you're going to run out of memory. And so while the solution is simple in the sense of like, just make more processes to make sure they all are running so that there's never any wastage, or you have to consider the fact that you may actually run out of memory. And so this comes back to something that I kind of mentioned very briefly in the beginning of the lecture. You don't have to load an entire program into main memory to be using it. You can actually load pieces of it. So if you got a program that takes, 10 megabytes of usage in memory, you don't have to load all 10 megabytes at once. Especially if you just, think about like just 10 megabytes of instruction and maybe 100 megabytes of actual data. Okay? At least for the instructions, you probably only have to load in the first third of the program. So maybe you load in like 3 megabytes of it. Why? Well, that comes back to when we talk about caching and the principle of locality. If you're running an instruction right here, spatial locality tells us that you're going to be probably running an instruction down here next, or maybe the one before it. But the point is, you're not going to just randomly run an instruction over here, unless you're using a goto statement, which is why they're bad in the first place. Alternatively, with the data, similar thing can be approached. You don't have to load the entire data. Maybe just load this part of the data. And again, with spatial locality, if you're using this line of code, you're probably going to be using this. And so and you can predict that when you're getting here, maybe you want to load a little chunk here. And temporal locality also comes into play. If you were using this data recently, you're probably going to be using the same data again. So keep that in memory, but you don't need to load other parts of the thing. Same here with temporal. So principal locality can be applied to figuring out what pieces of a program you should load, and you should only load parts of the program. And so the solution that I'm kind of talking about is referred to as swapping. I believe it's swapping. Here, figure 9.12. Yeah, swapping. Yes, swapping indeed. So another solution is swapping, depicted in figure 9.12. These are brought in one at a time as space becomes available. Well, I guess swapping is not just bringing them in, but also the fact that here's the thing. Let's say that your main memory can hold to make math easy, let's just say it holds 200 megabytes, maybe 256 because it's a power of 2. Okay, so you can hold 256 megabytes of memory. And so, you know, what you can do is you can load in maybe, let's just say, to make the math easy, let's get rid of the data. Let's just say that the 10 megabytes is including both instructions and data, and that the whole program is 30 megabytes, okay? And so we're gonna load in 10 megabytes, and there's a piece of data here and a piece of instructions, okay? So we load that into here, into memory, and that's gonna take 30 megabytes. And so that means we can load in about 8 of these, because 3 times 8 is 24. So about 8 of these into main memory, right? And so we got about 8 of these stored in main memory. And so that means that we can feed into our processor 8 processes. And so what are one of the issues here? Well, the issues is that imagine that the processor requires an address for the next instruction that isn't loaded into our main memory because it's outside of the block that we brought in. Well, then that's kind of like a miss. You know, when you think about cache misses, main memory misses as well. And what you can do is you can load in another piece of the program. So maybe load in this part of the program. Now, you can do one of two things. You could replace another one that you have here, or you could replace the same one for the program. So like replace the top part with the bottom part, or you can load these both in different pieces, right? So there's different ways that you can do this. Now that's, I think, what the book refers to with the swapping, okay? However, swapping is an I/O operation because you're reading it from potentially a hard drive into main memory, and it's slow. And so you got to figure out if this slowdown is worth it. And typically it is, because again, if you do prediction correctly, and if you do if you do page, what this is eventually going to be basically paging. If you do paging smartly, then you can have a bunch of little processes in main memory, or pieces of the process's code, of the program's code in main memory, that you can feed in so that your CPU is busy, and you avoid having all these misses by smartly taking things in and out. So like if you know that this process is going to be next in the queue, then you want to make sure that it is here. If process 5 is going to be next in the queue and it's not here in main memory, then you want to take it out of the queue or put it back in the queue while you load in that page into main memory. Okay, so that's basically what you do. And so there are two ways of doing it, and those are called partitioning schemes. And there's fixed size partitioning, and there is variable or unequal size partitioning. The easiest one is going to be fixed size, which is what I did there. So like you split your memory into little blocks of like 8 megabytes or 30 megabytes or whatever, and then you're going to load in pieces of your program into there. The alternative option is to have variable ones, where like there's one that's 2 megabytes, there's one that's 4 megabytes, there's one that's 8, and these are like specific increments. They're not just random. Like you're not just gonna have like a 1.5 megabyte thing here. No, they're well defined. Because here's the thing: to make life easy for the whole loading and saving thing, is when you're loading your program, you're gonna load it in these specific chunks that are the partition sizes. Like you're not ever gonna load 9 megabytes of your program. You're gonna load 8, or you're gonna load 16 if you have fixed size partitioning. Okay. Now, what if your program is 10 megabytes? Well, then too bad, because you're going to be still using up 2 slots of this. So you're basically using 16 megabytes of memory, even though your program is only 10 megabytes, because you can't share a partition. It's kind of like if you think back when we're talking about SSDs and NAND versus NOR memory, and essentially how flash memory, it has to be deleted in blocks. Same thing here. You can only deal with blocks, and you can't just put 2 programs in the same block. Why? Because by having these specific size of blocks or pages, you can load in the next page from the program back and forth, and make that a relatively easier process to figure out what to load next. So that's why there is the alternative of this variable size partitioning scheme, because then you can take advantage of, like, you know, using maybe the so this one's 8 and this is 16. You can maybe load this one in and load this one in, and that way you don't waste space. But that makes the organization a lot more complicated. So I'm not even going to talk about this method anymore. I just want to make you aware that there is an unequal size partitioning scheme that they'll talk about in 370. Let's just talk about the one where everything is even. So in the one that's everything is even, let's just make another square here that's not as messy. And let's just split this. It can hold 4 partitions, okay? And they're fixed size, so we don't really care. We'll just say that they're all 100 megabytes each. And you have a 512 stick of RAM. Maybe the rest of the main memory is for the control, okay, for the monitor, okay? So that would be the like 112 megabytes. That's your control. Nobody touches that. That's allocated to that. So here you got 4 slots. So what you do is, let's say you're gonna load in process 1 and you're working in that, and then you got another process that's gotta run, so you load it in, and then maybe another one, process 3, and now they're running, you know, and the process 1 and 2 are in IO. So then you're like, ooh, okay, these 2 are in IO, and now I'm about to start running 3. What if this guy goes in IO? So maybe let's load in process 4 if there is one that's waiting to run that was like, you know, has been started, and you load it in there. But now you got also process 5 that's ready to go, okay? So at that time, process 3 is in IO, and now process 4 is running. And you're like, oh snap, these are all in IO. But then you get lucky, and then this guy finishes at some point while you're running this one. And then this goes in IO. So you're like, whew, okay, well now we're running this one again. But you still got like 3 of them in IO. So what you can do is, you can take one of these out of main memory into the hard drive, and then bring in a new one in there. And again, it's not an entire process. It's just a piece of it. Because like process 1, you know, could be made up of like, let's say 402 or 401 megabytes. Okay, so you're only loading in maybe this part of it, and then there's other pieces. And so what you will end up doing is, the next time you run it, you may want to load in this piece again. So that let's say that at this time, you know, you're running process 5 that you just brought in, and then that one finishes, and then you're running process 1, and you're doing all these processes, right? But at some point in time, you are going to eventually finish running all of the pieces of the main memory here. And if you're getting close to doing that, then the scheduler might be like, ooh, okay, he's almost finished running this segment of the code. So maybe process 2 is still in IO at this time, so we're gonna kick process 2 out, save it back in hard drive for now, and maybe in there we're gonna put in process 1, but like part 2, okay, which is this part here. And that way, you know, the next time it runs, process 1 runs, maybe it finishes this and it starts doing this, but it's already available. So this is nice. It's happy, you know. And then because this finished, maybe now it'll kick this out and maybe throw in process 3 back in and have that ready to go. And so as you can see, it's trying to basically have as many things ready to go that are not waiting in IO. And that may mean taking pieces out, putting back in, and more importantly, putting them in different spots in main memory. So now you should be panicking at this point because, you know, when we're writing code in C++, we have specific memory addresses, right? We go ahead and say something like int ptr, you know, and then we say new int. And if we go ahead and see out ptr, you know, we get some address on the heap or something that is like that, right? And so the next time you're running a program, or sorry, the same time you're running a program, but the next time it goes into the time slice, it might be in a different part of memory. And so you're expecting to be in that spot in memory, right? Well, yes, but then again, that memory that you're looking at is not actually the physical address that you would find in memory. Because as you can see, because of the paging system that we've implemented here with swapping, the process's memory, first of all, it might not all be in main memory, including data, because again, we hear mixed data and instructions, but like this could have some data in here and also some instructions potentially. And again, it might not all be in the main memory, and it might be in different places in main memory every time it's running, because it's like flipping things back and forth wherever they fit. Because of this, the memories that you see as a programmer are not the physical addresses in main memory where they're stored. They're actually the logical addresses. Physical addresses, just so we're on the same page here, is the actual location in main memory where something is. So like this, you know, could be some specific address. That is the actual physical address, and you never see that as a programmer. The only person who sees that is the operating system, okay? Unless you're doing segmentation, but forget about that. So you never ever see that. You see a logical address. A logical address is basically a location relative to the beginning of the program. And so if this is like, if you're running like the 5th instruction of your program, then you see like a 5 per se, or you know, or the numbers might get shifted a little bit, but you're seeing still the address of the beginning of the program plus the shift of the instruction or data, you know, if it's an array or things like that. Pointer arithmetic, essentially. Okay, and so what goes down here is that when things get inserted somewhere else in main memory, so like, you know, let's say that at this, you know, P3 gets put here at some point. What you do is you get the physical address here, and then you add the logical address, and then you'll be able to get the next instruction that you're going to run. And this is a little bit complicated. Again, they do talk about that in 370, but essentially what that means is us as programmers are only seeing virtual addresses. They're not the real addresses that we're seeing, and that's okay, because if we did, we would break things essentially by trying to do pointer arithmetics when things get potentially moved around in main memory. And so as long as we have, and for this here, let me pull up the PowerPoint. So here's an example of logical. Here's, for example, first of all, an example of the of logical, physical, and base address. Base address is going to be the starting location of the process. So like right in the beginning of this, the first instruction of that process, okay? Which is going to be the top page per se. And from there, you know, if you have instruction 10, then it's going to look at the physical address of wherever that first page is, and then add 10 to it, and that's going to get you that. There is this picture here. So we have the page number and the relative address within that page. Now, each page is going to be each piece of the process that is being split up so it can fit in memory, which is split up in pages. And so, essentially, you know, if you have page 1, which means it's going to be the first part of the program, and you have address 30, then if you're trying to figure out where that is actually really in main memory, is you're just going to do the math of finding out where page 1 is in memory, where the address of that is, which is address 13 in this case, and then you're going to add 30 to that, which means that it's probably going to be somewhere in, well, I don't know if this is hexadecimal or whatever, but it's going to be the 13th line of that page, okay, whatever that address is in physical. So if this address 0x110, then the next one's going to be at 0, then address 13 of that would be at 0x10 D, I guess. Yeah, D, because it would be 9, and then 0 is 10, A is 11, B is 12, C is C for 13, I guess. Okay. Well, if we're counting from 0 or are we counting from 1, though? That's a real question. But anyways, you get the idea essentially. So yeah, that's what you see. That's virtual memory essentially. That's it's how the OS, and this is all handled by the OS, so you don't have to worry about any of this, which is why we've never talked about it in a programming class if you know in 135 or 302 or even 302 if you're taking it, because this is all handled internally. You don't need to worry about all of this at all. That's the beauty of the OS. It's going to figure out the resolution of where these things are located in main memory, and it works because, again, as I said, principle of locality. Basically means that you don't really need an entire program in main memory, or you don't need the entire data of the program in main memory. You just need pieces of it. And if you have a miss, then that's okay. You just load it in from the hard drive. And by the way, typically if you do have a miss, because it does take time to load it from the hard drive to the main memory, you will probably be taking out of the CPU and put into IO wait while the page gets loaded in. And then that also does bring up a problem called thrashing, which is when, imagine that, here, picture time, so I'll go back to this. Imagine that you have a situation like this, okay? You only have space for 3 pages, and you got a lot of processes running, right? And it turns out that you need to have page 2 and page 1 to be able to run your code, okay? Because it just keeps going back and forth between these 2 pages, like the instructions, because you're a coder and you did a go-to statement or something, okay? And so, you know, you got your hard drive, which has like pages 1 through page 8 or something. That's the number of pages that the program has. And so your CPU, you know, you got your CPU that's running, and then request something from here. Obviously, I'm not even introducing the concept of cache in here. You can see how that even makes it more complicated with cache hits and misses and paging. Yes, that's your future in 370. But still, ignoring cache and again taking cache out of the equation, we request something from page 1, which is here, and then we request something from page 2, which is there. But then in the meantime, we got scheduled out, and then other processes got scheduled in. Maybe process 3, which was ready to go, but then process 3, process 4, process 5 all took up memory. And then eventually you are about to come back in, so process 1 is there, page 1 of process 1, so page 1, and then you go in there and you need something from page 2. So then you're like, I need something from page 2, and then you obviously get put on wait, so then other processes go in there, and in the meantime, page 2 gets loaded here. But because of the high usage, page 1 is gone. So you go to page 2, and you run one line of code, but then you need page 1 again. But that is no longer in memory, so you get put on hold again. You can see how this can be a big problem, because you're only running one tiny little instruction every time, and then you were waiting a bunch of times. Because you're like, I really need both of them to be in main memory. Or what's even worse is imagine that, now this of course a good scheduler should avoid, but imagine that you need page 2, but before you even get set to run, page 2 gets kicks out again, at which time it's your turn to run and nothing is there. So then you're like, oh, okay, you can't run, go back there. And then by the time you load it in again, it gets kicked out again, and then you get run again. I can see that's a bigger problem. We're not talking about that. We're talking about more of a situation where you need 2 pages, and back and forth, you keep losing one or the other one. And so when another page is thrown out, every time you bring a page, you got to throw something out. And so if you throw out something right before it's going to get used, that's a problem too, And so that is basically thrashing, and that is when you're spending most of the time swapping pages rather than executing instructions, and that's what you're trying to avoid, okay? So that's bad. Don't do that. Again, that is something that hopefully the OS with branch prediction can avoid, but also as a programmer, that is why we don't do weird jumps and go-to statements out of nowhere, because that kind of thing can happen out of that. So yeah, that's virtual memory essentially. As a summarized quick version, is the idea that we have this physical and logical addressing systems because we want to be able to take advantage of paging. And again, the reason why we're using paging in the first place is because we want to be able to have a bunch of processes in main memory that we would normally not be able to hold. Because again, if our main memory can only hold like 500 megabytes, and then like a program takes 200 megabytes, on average, then we can only hold about 2 full programs before we run out of space. But by introducing paging, we could potentially hold an unlimited amount of programs in main memory. Well, I guess the size of the pages, if each page was 1 program, and still basically be able to have all these processes running so that the CPU is never in a situation where it's just waiting on I/O with no other process that can run. Furthermore, with the concept of paging, you can run programs in a computer that would be bigger than they could fit in main memory. So like if my main memory is 1 gigabyte and I got a program that requires 2 gigabytes of RAM, that's okay. I can still run it with the paging system because I only load, let's say I load in 512 megabytes of the program, run that, and then when this is finished, I can kick this out of memory, load in the second part, and then run that. And while that kicking out and loading is going on, I can run another program so that I don't waste the time. It's still gonna make my program a little slow because I gotta kick something out and put it back and put something else in. But at least I can do it, right? At least I can run a program that way. I'm not forced to try to access directly from the CPU because I may not have the circuitry required to be able to access things from a CPU directly. I can only access things from the CPU can only access things from main memory and not from a hard drive. Okay, so that allows me to essentially be able to run a program that requires more space than I even have to run in main memory. If you ever run into a situation though where you have, you're running a game or something, or you're, editing a video and you're rendering, and you ended up using more RAM than you had, you may have heard about something called as a swap file in Linux or things like that. The swap file is like extra space in the hard drive that is like fake memory, which can be used to kind of solve this situation where if you run out of memory space, it can actually use a piece of the hard drive as main memory. Of course, it's going to be super slow and painful, but hey, at least the program is not going to crash and can still run, even if it's really, really, really slow. So that's essentially what they mean when they talk about the swap file and so on. And again, it gives you that flexibility to be able to run programs that would otherwise not fit in main memory, which means you wouldn't be able to run in the first place. Something kind of cool here. I opened up Task Manager. I found how much cache I have: 256, 1, and 8 megabytes of L3 cache. Logical processors. The word logical, so versus physical. And then you can see number of threads here, which is kind of neat. But I was gonna say, if you click on memory here, you can see how much memory I have in use, how much it's available. But you look at here, it says page pool and non-page pool. That's talking about paging. So now you know what that is. So yeah, just thought I'd show you that, which is pretty neat. And then you can see on my disks as well. So this, of course, is one of the things that we want to know what to do, right? That accounting that the book says is monitoring resource usage. And if my memory was to run out, I can use my hard drive as extra space in case of, per se, an emergency. But of course, that is painfully slow, and you don't want to do that, ideally. But hey, better than crashing, I suppose, if you're running something critical that you don't want to just shut down. So just to give you a formal definition from the book of virtual memory is, because a process executes only in main memory, that memory is referred to as real memory. But a programmer or user perceives a much larger memory, that which is allocated on the disk. This latter is therefore referred to as virtual memory. Virtual memory allows for very effective multi-programming and relieves the user of the unnecessary tight constraints of main memory. So there you go. The rest of the chapter, there is a talk of segmentation. Segmentation is an alternative to paging. They don't have to be mutually exclusive. Intel x86 has both segmentation and paging, but basically paging is invisible to the user, right? You don't see this whole like how this like thing gets, which page gets loaded and whatnot. You don't ever worry about that. And you got your logical addresses to hide physical addresses and how they get moved around whenever pages get moved around. So you don't see any of that stuff. However, there is another system which is known as segmentation that is visible to the programmer, and is provided as a convenience to organize programs and data, ideally as a mean of associating privilege and protection attributes with instructions and data. It allows basically to the programmer to see the memory, which consists of the multiple addresses, spaces, or segments, and they can be dynamic in size, and the programmer or the OS will assign programs to the different segments. As to the why you would want to do such a thing, is you can look at the end of the section. There's a list of advantages, in which basically it lends itself to protection, it lends itself to sharing among processes, and it allows the program to be altered and recompiled independently without requiring that entire set of programs to be relinked and reloaded, and it simplifies the handling of a growing data structure. So basically, you lose convenience to try to gain efficiency by manually handling how things are loaded in and out of memory. But again, that's beyond the scope of this course. 9.4 and 9.5 give you the example of how this stuff with memory is handled. With paging and addressing is handled in x86 and then ARM. So I will let you guys just look at that on your own time and read it and kind of get an idea. But again, don't feel too bad if a lot of this goes over your head. I won't focus too much on the test about this, other than at the very basic level, because again, this is something that you will really learn in 370, and you need an entire course to be able to understand. I recall having different ways of computing physical addresses from paging offsets and things like that, which and then that's the things they put on the test then. So yeah, but it's a cool class. They also add in a lot of concurrent programming into that class. They talk about race conditions and things like that. So yeah. So anyways, that concludes the discussion on chapter 9, which is what this is. Okay. So we talked about the operating system and an overview. the different objectives and functions of it, the types of them. We talked about scheduling and the different schedulers that they have, like long-term, medium-term, and short-term scheduling, which is also known as a dispatcher. We talked about memory management, swapping and partitioning and paging, virtual memory a little bit, and I just very, very briefly told you that there is this thing called segmentation. And yeah, that's pretty much what we did. And so now, for the remainder of the lecture, we are going to be talking about chapter 10, and this will go very, very fast. So chapter 10 has five sections, and the first section is introducing to you into what the decimal system is. I would be surprised if you've never heard of the decimal system before, because that's what we use when we are talking about in math, and that means it's a base. You know, all systems have a base, okay, or a radix. That's another nickname for the base. And that's basically the range of symbols used to represent these numbers. And so in this case, our base is 10 because we have 10 symbols. We have this symbol, this symbol, this symbol, this symbol, this symbol. Okay. There. Those are all the symbols that we use, right? And there's 2, 4, 6, 8, 10. 10 symbols, okay? Once we want to represent the number bigger than the last symbol, we use a mixture of the first symbols. So we basically, you know, we could put this as a bunch of zeros, and then eventually the biggest number that we can have is a 9, and from there we reset back to the first symbol, which is a 0, but we change the next significant digit to be the next symbol, which is a 1, right? This obviously you're like, what? Very complicated way of saying how to count to 10, but the idea of this is the concept of a most significant digit and a least significant digit, okay? The least significant digit is this one's over here, the most significant ones are to the left, and this makes more sense when we were talking about like binary, because in binary, you know, that is something that we're not totally, well, we are CS people, we are familiar with it, but like at least at some point we were not familiar with it, right? And so, you know, in this counting system, we only have 2 symbols to count. So the changing of the digits happens quicker, because already when we're counting to 2, we're changing the second digit here to a 1. And then when we get to a 4, you know, because we got 0, 1, 2, 3, and then 4, we need to change the third digit, you know, to a 1, and so on. So essentially, that's pretty much what the first 3 sections of the chapter talk about. And then they talk about a form of converting binary to decimal. I hope you learned this in CPE 100. Again, the easiest thing to do is you can think of this as powers of 2. So if you got a value, like I'm just picking this out of randomness. If you want to compute it to decimal, you can look at these as powers of 2s. So you got all of these lines here. Regardless of what they are, they're powers of 2s. And you start with 2 to the 0, to the 1, to the 2, to the 3, to the 4, to the 5, to the 6, and to the 7. And if you got a 1 there, actually take that power. If you got a 0 there, don't take that power. And so basically 2 to the 0 is what? What's any exponent to the 0 power? It is going to just be 1. And so it means you can have a 0 or a 1 there. And so if you, and by the way, there are calculators online that you can do this. So hopefully on the test you're not like trying to really do this by hand. But it's a good thing to basically be able to know, right? First of all, I guess always remember that any exponent to the power of 0 is going to be equal to 1. And so if you got a 1 there, you're going to add a 1 to that. 2 to the 1 is just 2. 2 to the, here, let's just compute these powers first, which you should frankly know them by now by memory. So 1, then 2, 4, 8, 16, 32, 64, 128, 256, and 512. And I think we have enough now. So this is 2 to the 0, 2 to the 1, 2 to the second, 2 to the 3, 2 to the 4, 2 to the 5, 2 to the 6, and 2 to the 7. That's as many as we need. We don't need these. And so if you're trying to convert this into decimal, anywhere that there's a 1, add it to your final answer. So we're going to add this one in. We have the 5 1 we're adding in. We have the 3 we're adding in. And then we have the 1 and the 2. So basically add in 1 plus 2 plus 8 plus 32 plus 128, which should basically give you, this gives you 3 plus 8, which is 11. plus 32, which gives you 43, plus 128, which is going to give us 7 here. So 171, I think. So let me double check my math. Binary to decimal calculator. Rapidtables.com. So we had 10101011 convert 171. Yay, we got it right. So yeah, that's how you convert. If you want to do it the other way around, if you want to convert from decimal to binary, just do this process backwards by figuring out, take the biggest power of 2 that can fit in here, and use that and subtract that answer. So like let's do a different number. So let's pick a number like 6. Oh man, maybe I should pick a smaller number. Let's pick 225. Okay. And so if we want to convert this into binary, pick the biggest power of 2 that fits in that. So we know 128, and then we know 256. 256 is too big. So we're going to pick 128, and we're going to subtract it from that. So what is 225 divided by 128? I don't feel like doing math, so I'm just going to type it. 225 minus 128 is 97. So we got a 97 remainder. So now we got to pick the biggest exponent that fits in that. So we got 32, 64, and then 128. So 64 will fit in that. So let's subtract that from 97. So 97 minus 64 is going to be 33. Okay. So and remember what we did. So we got a 128 in there, and we got a 64 in there. Now we got a 33. So do the same thing. That actually fits in 32 very nicely. So we're gonna put in a 32, and then we got a 1. Okay. So all we gotta do now is put the exponents to that. So what was 2 to the, that was 2 to the 7, right? 128. Yeah. So that's 2 to the 7, 2 to the 6, 2 to the 5, and 2 to the 0. Which means if we want to put the binary representation of this, we are just going to go ahead and put a bunch of zeros all the way to 7, and then change them to 1s for any of the digits we see here. So it's 0, 1, 2, 3, 4, 5, 6, 7. And so now we're going to change these to 7. So here, let me put the number so you can see it. 6, 5, 4, 3, 2, 1, 0. These are powers of 2s. So basically, we are going to change. Here, I'll highlight them first. We'll change that one because we have this one in here. We're going to change this one, and we're going to change 2 to the 32nd, the 32, which is the 5. This one, and then 2 to the 0, which is this one. So we're going to change those to 1. So there's going to be 1, 1, 1, 0, 0, 0, 0, 1. And there you go. Now let's go ahead and confirm by plugging it into my binary to decimal calculator. So 1, 1, 1, 0, 0, 0, 0, 1, 225. Is that what I had? Yeah, 225. Yay! So I got it right. So there you go. That's CP100 for you. If you need more help with that, you can go ahead and look at that section. Go ahead and read the fraction part. I'm not going to do the fraction part because I have no purpose for that. But last but not least is hexadecimal. With hexadecimal, I think the TA kind of talked about it a little bit. Basically, it's convenient sometimes when you're trying to talk about like 32 bits, you know, it's a lot of zeros and ones to put in. It's kind of painful. So you can summarize that by using hex, because you can basically take 4 digits in binary and turn them into one single digit in hex. So like, for example, if you got the following, and this I have a table, 101, 1010, this becomes A in hexadecimal. And so if you got a binary code that's like this, you know, this is 4, 8, 12, and 2. That's 32 bits right there, okay? Or 4 bytes, essentially. Oh, no. It's actually 16 bits. It's 4, 8, yeah, 16. So this is 16 bits, or 2 bytes, okay? It's a lot of zeros and ones to write. Especially, imagine now I'm gonna do this for like 32 bits, right? So instead, you can do the hex representation of this. The hex representation of this, looking at the little table on page 340, it's just basically the number, but again, I don't feel like doing math. So this one's going to be 6. This one is C. this one is 1011. That would be 1011B. And then that should be 3 right there. Yeah. And so it's a lot easier to just write this than it is to write all of this. Especially when you're talking about in main memory, there's 32 bits, you know? So that would be twice this. Imagine that it was just the same thing twice. So like, let me copy paste. Suppose that you have the following address in main memory. In a main memory that has 32 bits, which is 4 bytes, it was just literally this twice. That's a lot of zeros and ones to write. It's a lot easier to represent that in hex, just to basically save your hand from writing that much. So that would be the hex equivalent. And the usual symbol to signify its hex is you put a 0x. And that is why you see addresses in hex in your computer, because it's just less digits to write. Hexadecimal. And yeah, that's pretty much chapter 10. So that will conclude the lecture for today. We definitely covered quite a lot. Hopefully it's not too long. And if it is, then I guess I won't do a lecture for tomorrow. I'll have to figure that out. I do want to cover chapter 11. I think chapter 11 will be a short lecture tomorrow, because the biggest thing I want you to take out of that is how floating point notation is done in properly. You know, IEEE standard for that. You should have no, and maybe talk about that. Well, you probably all know two's complement, but I guess I'll bring it up. So yeah, that should be a quick lecture, I hope. I'll probably record that actually right now once I finish this. But yeah, keep up to date with the Discord and Canvas, and I hope that, you know, I really tried to cram as much possible information here, and while making it easily digestible, of what an introduction to operating systems is like. Again, you will revisit this stuff when you take CS 370, and you know, come back and tell me how it goes, and tell me if this intro helped, or if it just made you more confused when you take that class. So until then, until next class, hope you guys have a wonderful day, and take care. Bye.